So welcome back, everybody. I'm sharing my screen now. So, okay, so there will be no class on Wednesday, just that everybody knows that. I have changed the syllabus accordingly. Our last class is on the 27th of December. That's going to be the review class, the review for the finals. From the 28th until the 4th or so, I mean to say that you have some kind of study week and reading week. So we're not interfering with that week. So I do the last class on the 27th. The syllabus contains the exact same amount of classes that I always taught. And I think we're in a good course that essentially we can drop Wednesday. Before the holidays, it's going to be the last class is going to be on the 20th, and then one more after the 27th. That gives you a week to digest everything, accumulate your questions for the review class. And then we can go through the material on the 27th. We talk about the application of methods the last time. And yeah, then we have, let me quickly look at the syllabus. So how are the discussion topics going? They're interesting. They get a little more interesting now. They get a little bit more esoteric, but they're increasing now in terms of applicability in our daily routines. So as said here, we're continuing today with Anova. We're reviewing, likely we will not only review, likely we will actually do the within groups Anova we're going to do next week on Monday. And then on Wednesday, we jump over to correlation. Quiz 2 is covering T distributions and Anova. Quiz 2 essentially will not cover the two-way between groups Anova. So we're only doing one way between groups Anova and one way within groups Anova. We're not doing the two ways between groups Anova, because I think this is beyond the scope of an introductory class. So we're doing a review then next week on Monday. Then we switch over to correlation and linear regression. We're going to practice this on the lab day on the 15th. And then we do on the 22nd, we do our chi-squared test. It's not the 20th, it's the 22nd. On the 22nd, we do chi-squared test. This is the only non-parametric test we're going to do. And then we have a review class on the 27th, as mentioned. The final exam is on the 7th. I believe it's at 1 p.m. So that should be easy to accommodate in your schedule. So we have. No, it's in-class. No, I'm not allowed to. Explicitly received the email from the dean. I'm not allowed to. Unfortunately, we got to do it in class, and it's got to be at the same time. If you request separate accommodations, this needs to go by the office. No, the final. It's an in-class quiz. It's actually, I'm not even 100% sure I'm going to do this. I actually got to speak with the dean's office. It's actually the 7th. That's what is that, like Monday? I'm not even sure I'm going to get that into my schedule. That's a whole different conversation, please. Yeah, I got to work on that. Good. All right. So that's it. That's the administrative stuff. Practice lab 3 is due on 11/28, so it was yesterday. So please submit it. Didn't yet. Homework 2 I posted earlier. That should be accessible now for everybody. And well, that's basically the T distribution and the T statistics. Quiz 2 next week, Wednesday, on the 8th. Homework 3 will then be posted the week after. All right, so that's this. So enough of this. Let's get started with theory. We are doing Anova now. Okay. So we are starting off. So Anova is essentially the analysis of variance. It's called that way because the mainstay and what you're using for hypothesis testing is actually the variance between groups and within groups. So what does that mean? So now you essentially, we have discussed now the scenario with the t-tests where we have one scale variable that essentially is the dependent variable on the y-axis, and we have a nominal variable that defines the groups, right? These nominal variables was male versus female, randomized into a trial and intervention group, not randomized into the intervention. So basically, these were two separate groups, two independent groups that were compared to each other, whatever that distinguishing nominal variable was. So now we are going a step further. We're using the F distribution now, where we're basically working with 3 or more groups. So now the nominal variable has at least 3 levels, which we see here, for example, here on the right. We see a likelihood of a collision while merging into a lane, where you have the smallest probability of a collision when you drive alone, a somewhat higher likelihood when you have a passenger next to you, a co-driver next to you, even higher when you have a video phone, and the highest when you have a cell phone. That's a weird example because I would expect the video phone to distract you even more. So essentially you have more variables, more levels in your nominal variable. So you have more than 2 groups, and that's 3 or more. So you can use, for that purpose, you can use the Anova to do this comparison between these groups. So the obvious question you're going to ask yourself now is like, why not do a t-test? If you have 3 groups, you can compare group 1 versus group 2, group 1 versus group 3, group 2 versus group 3, right? Same thing. The problem is with each of these tests, you have a hypothesis test, a full hypothesis test that comes with a type 1 error. As you remember, the type 1 error is the error of you rejecting a hypothesis, a null hypothesis that you shouldn't have rejected. So this type 1 error is our alpha on the sides, 2.5% on each side. It's the probability of this being from the same distribution, but you rejecting it by random chance. So the problem, if you do more than one t-test, this alpha is an independent probability for each of these t-tests. So if you see on the next slide, you essentially have with every comparison, you have with one comparison where you have 2 means that you're comparing to each other, you have a probability of 5%. If you have 3 means, your probability of a type 1 error is basically exponentially inflating to 14%. You're doing 4 comparisons with 4 means, you actually need to do 6 comparisons, and then your probability of a type 1 error gets up to 27%. So that's more than 1/4 of a probability that you're rejecting something due to chance only. So you want to avoid that. And for that reason, we're essentially using the so-called F distribution. So the idea that they're trying to outline here with the Swiss Army knife is, so you have this STAT test, where you're basically comparing one sample mean to your population mean, a known with a known distribution. Now you're basically inflating that to 2 distributions, to 2 samples with the t distribution. And now you're basically up to more comparisons by basically using the same population, but you're separating them by their distribution characteristics of whatever distinguishes them according to your nominal variable. So all 3 of these tests, all 3 of these distributions have an underlying idea, which is the normal distribution curve. So all of them do have the assumption that they're normally distributed. So now when you connect this, you essentially have with a STAT test, you have one sample. You have one sample and you calculate the mean of that sample. You compare it to your population mean mu, but you do know the sigma. You do know the standard deviation of your population, which is unfortunately not true in most cases because you only have a small little sample available. Remember that the reason for the birth of the t-test, which was essentially the Guinness brewery, where they took little batches and they used this as little sample populations, and they estimated the variability of the quality of the beer based on these little batches. And by that, they compared it to the overall desired quality level of the overall B that they wanted to achieve. So if you have one sample and you only know the mu of the overall population, you estimate the variability from the T, from your sample, using the T distribution. You can do a one sample t-test. You have two samples, you can compare them under the assumption that you randomly sample repeatedly and you get either a distribution of the means, a distribution of the mean differences, or a distribution of the mean difference. For the paired sample t-test, you can employ t-tests. For the F statistic, you have 3 or more samples that can be used with 2 samples. Okay. So what you essentially do, you're comparing the variability to compare those means. So the F is in essence nothing else but the variance between the groups. So you have now more than 3 groups, 3 or more groups. So you get at least three different means. And these means do have a variation, right? They do have a variability. So if you have 3 different means, you get a variability by the means alone. So this is the variance between groups. This variance between the groups is not divided by the variance within the groups. So each of these groups has variance by the numbers contributed within each group, right? So now as a little memory helper, the variance between groups is always going to be larger than the variance within the groups, as we know, because within the groups, within the groupings, you have larger sample sizes that decreases the variability. But between the groups, the variance is going to be larger. Therefore, the F statistic essentially is always greater than 1, or not always, but in many cases greater than 1. So you're looking at a rather larger value, right? So it's large variance divided by the smaller variance gets you to an F. So the difference among the sample means divided by the average of the sample variances. And these variances are, so between group estimate of the population variance based on the differences among the group means, within groups, estimate of the population variance based on differences within sample distributions. When it comes to nomenclature, you distinguish between a one-way Anova and a two-way, three-way, four-way Anova, where a one-way indicates that you have one nominal variable with more than 2 levels. So when you think of the driving conditions, there was the likelihood of a collision with driving alone, driving with a passenger, driving with a co-driver, driving using cell phone or using video phone. So these are 4 different levels of that nominal variable. Between group in this context indicates that you have 2 different samples, or 3 or more different samples that you're comparing. So this nominal variable splits now the entire population in 3 or more groups. This is a between groups Anova. The within groups Anova follows the same principle. So you have more than 3 groups, but you have multiple entries for each participant. That means, let's say, for example, you have that likelihood of collision estimated based on the condition of whether you have a co-driver with you or not. But the next day, the likelihood is assessed again, and next day you're on your cell phone, for example. So it's under differing conditions. You basically have, just like in the same fashion as with the paired sample t-test, you have before and after, you have a chronological difference, or some features that constitutes a difference between before and after different measurements. And you essentially will test within one individual several group conditions. That's a within group Anova. Any questions on that? There are some assumptions to Anovas. regardless of the type, they need to be randomly selected from a population. That's pretty much the main assumptions of all tests, that you have a random selection from a population, and this creates generalizable findings. And they're not in that group for some particular reason. You have normally distributed samples. The normal distribution is for the Anova as a parametric test, the most important condition. And that you have something that is called homoscedasticity. And this is a complicated word, and it indicates that the variance between the groups, so when you have variance for group 1, variance for group 2, variance for group 3, and 4 and 5 and 6, does not differ more than the different recommendations. It should not differ more than 20%. Is a considerably conservative assumption in this context. So the variance needs to be comparable between the groups. This is also something that is important for correlation and regression, and I will come back there again. So again, it's called homoscedasticity. Homo meaning equal, so the same. Scedasticity indicating the variability over an entire range of comparisons. So all your groups need to have a comparable variance. Not the same, but comparable. So the opposite of homoscedasticity is heteroscedasticity, which indicates that there are differences in the variance. Homo and heteroscedasticity. So the hypothesis testing is essentially, again, the same. Nothing differs much. It's still a hypothesis. And we're not talking about the calculation as of now yet. We will in a second. But basically, it's the same as same 6 steps. So we're identifying the populations. We're identifying the groupings within these population. We're identifying the distributions. We test for the assumptions, which is random selection, normal distribution, and homoscedasticity. That means we need to do descriptive statistics. We need to understand the groups. We need to understand how many individuals in each group. So we're characterizing our populations. When we're stating a null and the research hypothesis, we're determining characteristics of the comparison distribution. This is when you do your variances, you calculate your standard deviations, you look at the distribution in histogram, so you're comparing them. Step 4, you determine the critical value or cutoff, which is to be found from the F-score table. Step 5, you calculate the test statistic. And 6, you make a decision based on the test statistics compared to the F-score table. It's pretty straightforward, right? There's nothing different so far. Okay, so now we're looking at example 12.1 in the book. So we're identifying the population distributions and assumptions for populations, F distribution, 3 assumptions, which we know already. And this is essentially to be found in the module for this example. Oh yeah. Okay, example 12.1. So the idea was to find out whether different communities all over the world have a different understanding of fairness. For this very reason, they had them play the so-called dictator game. I've never heard of it, but it's an interesting sociological experiment. So they basically, they gave the dictator in the game money, and he was able to either keep all the money or distribute the money amongst the other fellow players. So, so it was considered in that game fairer to give the second player at least 40% of the money than to give him or her only 10% of the money. So this is how they evaluated fairness. And they compared these scores in different populations. So one population was a foraging population. The other one was a farming population. I think it was in different developing countries. The natural resource populations which was also somewhere, I think it was in Southeast Asia. You can look it up in the book. And then industrial communities. So they found these different populations and they found fairness scores. So this is the underlying example for our calculation today. So we're going to calculate now, and following the example of Nolan and Heinzen, we're going to follow now these calculations. And they're fairly straightforward. They're not terrible. They look quite confusing, but they're not bad. And I'll walk you through this. So state the null and research hypothesis. So the null hypothesis of this is essentially that people living in societies based on foraging, farming, extraction of natural resources, and industry exhibit on average the same fairness behaviors. That indicates that these scores would not differ between those groups. Are you cold? Should we close it? Are you cold? Should we close the window? Yeah. Thank you. Appreciate it. I just wanted some fresh air when I came in. In the same context, the research hypothesis that there is a difference between these communities. So this is what we're going to be determining now. So for that, we're not working with sample sizes. So again, sample sizes are indicated with an N, whereas degrees of freedom are essentially what we use for our calculations. So we have degrees of freedom between, that's the number of groups. So that's the sample size of groups because we're calculating the variance between the groups, right? So the number of groups minus 1 gives us the degree of freedom between. The degrees of freedom within is the sum of all degrees of freedom within the group. So again, degrees of freedom within the group is calculated by the number of individuals in the group minus 1. Same principle applies then with the t-test. Degrees of freedom is always sample size minus the number of the groups. Good. So what is the degrees of freedom here? So we have now, for our example here, we have degrees of freedom between, that is 4 minus 1, right? So that makes a lot of sense. So this is degrees of freedom between is n minus 1, and this is 3. So degrees of freedom within is now all the n's. So this is degrees of freedom 3, degrees of freedom 2, 2, and 2. So it's 6 plus 3. So this is df1 plus df2 plus df3 plus df4. So this is 9. Good. And df total is now all added up together minus 1. So this is 4, 7, 10, and 13. 13 minus 1 is n total minus 1, minus groups, minus the degrees of freedom between. No, minus 1, sorry, minus 1. So that's 12. Make sense? Hello, how are you? So you use these calculations, right? You have degrees of freedom between n groups minus 1. It's 4 groups, minus 1 is 3. We have degrees of freedom within, which is we have degrees of freedom for group 1 is 3. For group 2 it's 2. For group 3 it's 2. In group 4 it's also 2. So that's 6 and 3, that's 9. Then we have degree of freedom total is essentially the total number of participants minus 1. Good. So now we're starting off with the first, and that's a little intimidating. And there's an F-score table that you have in your module. So the F-score table, it looks worse than it is. It's not that terrible. So the F-score table, essentially, you remember that you have variance between the groups divided by the variance within the groups, right? So the degrees of freedom in the numerator is your variance between the groups. So this is the number of groups on the columns, and you have the number of within in the denominator as the rows. So when you look then for degrees of freedom in the numerator 2, which is 3 groups, degrees of freedom of 3, which is 4 total, would here be represented by the respective p-value at which you want to test. So this is how you determine your alpha. You go down numerator, that's the groups. You go down the rows, these are your participants. And here you find the respective 10%, 5%, 2.5%, 1%, 0.1%. This is how you find your alphas. Notably, this alpha is to be found in this distribution. So when you calculate your F, you're testing your F against a unimodal right-skewed distribution that essentially has a long tail where you essentially will find your critical value. As soon as your F is exceeding the critical value that you determined in step 4 of hypothesis testing, you are rejecting your null hypothesis. And when speaking about null hypothesis, so this is the F-score table. So again, so now it's essentially, so they're basically presenting it in the same fashion. I just found mine better. So this is up to you. You can use that. Like it's probably fine for whatever. So there's one in the book as well. It's the same principle, right? Between groups, within groups, degrees of freedom. P-value, alpha level, 1%, 5%, 10%. It's just the other way around. It's just you need to follow just with the Z-score table and the D-score table, you just follow along and you find that particular cell that represents your critical value. Make sense so far? Yeah, you came a little late. It's just determining for an Anova, for an F-score table, how you determine your critical value. But it's being recorded, don't worry. Okay. So, but what are you testing essentially? So once you have this cutoff on your unimodal right-skewed F distribution, you are essentially, for our example here with our dictator game, we have a critical value of 3.86. So what are the degrees of freedom of our numerator? So we said 3, right? What is the degree of freedom of the within group? So you got to be careful. You got to go further down. You're essentially looking at a degree of freedom that is, let's look at this one. You have 5%. You're finding 3 degrees of freedom. And you have a within group degrees of freedom of 9. You remember how we had 3 degrees of freedom in the first group, 2 in the second, 2 in the third, and 2 in the fourth. Comes to a total of 9. So here 3.86. 3 degrees of freedom between groups, 9 within groups. Bless you. 3.86 is our critical value at an alpha level of 5%. So now the logic of the F statistic is essentially that they're comparing between groups variability over the within groups variability. So you have the variability between the groups, the means between the groups, and you're comparing it to the within groups variability given by the respective constituents of each group, and it quantifies the overlaps of these distributions. That's essentially what the F statistic is testing for. So you have 2 ways to estimate this variance with a between groups variability and within groups variability, and this is what we essentially need to quantify now. So what this means in the greater scheme of things, you have each group, so this is foraging, this is farming, this is natural resource, and this is industrial. We have with each group, we have a mean. This is the group mean. And we have for this chord here, a so-called grand mean. The grand mean is the mean of the means. Grand mean. And you're comparing, basically, you're comparing the overlap of your distributions with this grand mean. And this gives you an insight whether one of these groups is different. As soon as one of these groups is different, your p-value will be smaller than your cutoff value. And you can conclude with a 5% probability of making a wrong decision that one of these groups is significantly different from the overall distribution. That will prompt you to then further investigate. If your Anova is not significant, you conclude that it's insignificant. You don't need to do any further testing. There are no differences between the groups. So, any questions so far? It's fairly simple in a way, right? It's like you basically amalgamating hypothesis tests into one hypothesis test, and you say, okay, so this is not significant. I don't have to do any further work. That's it. We're done. To present this, you're using something that is called a source table. The source table allows you to amalgamate all these calculations. That's a little calculation intensive, let's call it that way. So there's quite a bit of calculations to be done. And the source table allows you to kind of amalgamate that in one little table, which you're going to be hating after homework 3, I guarantee you. So, but it's a good practice. It's important to know how to compute them and how to interpret them. This is really, really important because you may be using SPSS or whatever software. Hopefully you're going to use R. And the output of that will be such a source table. So the interpretation of the source table is really central. So a source table presents important calculations, gives the final results, and gives them in a format that is easy to read. It provides a convenient summary that describes the sources of numerical variability. What does that mean? That means that it shows you 4 main characteristics of your hypothesis test. It gives you the source of these numerical variances or variabilities. It gives you between, within, and the total. You have sum of squares between. And again, this is the same principle as the standard deviation. You remember when I said sum of squares, memorize sum of squares. This is going to haunt you. This is going to come back. And here we are. So this is the same as you have calculated with the standard deviation. It's the mean, and it's the deviation from the mean, and it's the squared deviation from the mean, and summed up to the sum of squares. Gives you the sum of squares between, the sum of squares within, and this adds up to the sum of squares total. Degrees of freedom, which is calculated, degrees of freedom between, degrees of freedom, which is essentially the number of groups minus 1, Then we have the degrees of freedom within, which is the degrees of freedom of each group summed up. And then we have degrees of freedom of total, which is the sum of degrees of freedom between and degrees of freedom within. And here we have the standard error of the mean, between, and within, which is essentially nothing else but the sum of squares between divided by the degrees of freedom between, the sum of squares within divided by the degrees of freedom within. This gets you to this ms between and ms within. And this, dividing this by this, gets you to the f. That's all you need to know. It's not terrible, right? So, three different types of statistical deviations: the deviations between groups, the deviations within groups, and the total deviations. We've just seen that, right? So now we need to know that. We need to do this, obviously. That's the next step. And therefore, we're going to do now exactly this. So we have now, this is the GM. GM stands for this grand mean. This grand mean is basically the mean of the means. So we're going to arrange now our data in this format as they have outlined here. We calculate the grand mean, which is essentially the mean of all these entries. Then we calculate group means. We're calculating the deviations of X individual entry minus the grand mean. And then we square this and gets us to our sum of squares. Simple, right? Not terrible. I see skeptical looks. Okay. It's not complicated. Okay, let's do this. So what we do now is we're taking now the first sample. Those are the first four. You remember how I always say paste special and transpose? This is what you're going to do now. This is foraging. Now we take these three. We go again, paste special, transpose. This is farming. Now we do natural resources. We transpose. That's natural resource. It's 47. And now we do industrial as the last. So now we calculate averages. Of these four entries, average of this, average of this, and an average of this. So this is a group mean. Take your time to follow along. Okay, so as said, it's a little bit more intense with the calculations, but it's not terrible. It's not difficult calculations. So essentially, you are transposing it. Are you on board with that? Did that work out? No? Okay, you need to make a right click and say paste special. It should be coming up. Check my distance. Just paste special. Yeah, and there's transpose. Transpose is the second one in the second row. No, second row. That's the third row. One up, up. That's it. No. No, it's the other one then. The third one. Sorry, my bad. Now the third one in the second row. Third one in the second row. Yeah. Yeah. All good so far? It's a fun exercise. It's a fun exercise. It's a lot of fun, right? Yeah, good. I'm happy you share the sentiment. Okay, average is then essentially, I find Excel really fun. It's like I always loved that. Okay, so we have now a grand mean, which is 39.385. This is our X. Now we do X minus GM. It's now this minus this, locking it in with the dollar sign, just like we always did. Now we get this list of deviations. Where are you? Did you? Coming along? And now, just like we did with the standard deviation, we're just squaring this. And now we want the sum of squares within, no total, sorry, total, because it's the grand mean. Sum of sum. Just gives us another 629.07. Yeah. Yes, yes, yes. Where are you? X minus GM. This is just the average of all these entries. Gets you to the grand mean. No, it's literally average, the average function. But yeah, to just average from the first to the last entry. So this is our total. So now we're here. Now we're going for the next calculation. Because now we need the individual means. Now we're getting the within group means and deviations. So now we have X minus M as being our deviation. So we have to calculate now, and this is a little bit more annoying because now we need to do X minus M, which is now this X minus this M. And if we're locking it in again, but now you're only allowed to go for the X within each group, right? Because down here, you need to change it again because it becomes now the X minus the next group mean. This is a little bit more involved. X minus this. You can't just like drag it down to different group. No, because then it takes the wrong group mean. You need to adapt the group mean. So it's a group mean for each group. So we have here 4 different means for each group. And we need to calculate the difference of the within group entries, the x's, minus the group mean. So that makes it a little trickier. Yeah. So there are ways how you could do it, but this is the simplest way. And now again, you sum this up. Oh no, you know, no, first you square it, x minus m squared. Is not this squared. Now the sum of square within is now the sum of this. $167.419. 19? What? They rounded. It's actually 19, not 7. Okay. All right. So the slight deviation on the second, no, on the third decimal is because they rounded more than we do. So them being Nolan and Heinz. So now you already know it's super easy what we need to do, right? So these are the calculations here in mathematic annotations. So you have sum of squares between is m minus gm, which we also could do at this point, right? It's like it's each individual m minus the gm gets us the variability within groups. So just for the sake of confirming, we can do now this minus the grand mean should essentially be this minus the grand mean this this minus the grand mean this gets us this these deviations. So that's m minus gm and m minus gm squared is not this squared. So the sum of squares between is now the sum of these 4 entries. It's 141. How can that be? Can't be 141. Ah. Careful with one thing. I know what it is. So when you do this calculation, there's a little caveat. Remember, I tripped over this already once. S4 to S16. Because you need to do this for every entry here, because otherwise it doesn't sum it up correctly. I tripped over this already once. That's the 461. So if you calculate, so there are several ways how you can calculate your between group, right? So when you look here at the source table, you have here the calculation of within groups was the second one we calculated. The total was the first one we calculated. So this one I calculated the last because this between sum of squares is also a resultant of the total minus the within groups. So you can calculate total minus within groups sum of squares, and you get to the between sum of squares. The calculation that I did now actually needs to be repeated and needs to have the same number of contributions for each entry. So for the degrees of freedom total. And they don't really notate this in the spreadsheet. Essentially, the way you would do this in your calculation, you would do, I don't know whether you ever seen this mathematical notation. You would have the epsilon sign for sum, and you would do from to. So on the bottom of the sum sign, you would have where you start off. That would be essentially n equals 1, n1, to n equals the total number of participants. So it's the notation is not really accurate. But essentially what we have now is basically our source table mapped out. So we have all the calculations we need. So we need now between, so this is source, between, within, and total. So now we have the sum of squares, we have the degrees of freedom, we have the MS, and we have the F. So now the only thing we need to do is sum of squares for between, we got from here. Sum of squares from within, we got from here. And this sum is essentially the 629 we have from sum of square total, right? So now we have degrees of freedom, which we have quantified here on the side. Degrees of freedom between is 3. Degrees of freedom within is 9. Degrees of freedom total is the sum of degrees of freedom between and within. If we want the standard error now, this is the sum of squares divided by the degrees of freedom. This here 153 and 18.6. And the F is now between divided by within. Is an F of 8.22. Yes.
What did you do for
The
the MS?
MS is K22. It's the sum of squares divided by the degrees of freedom. That's how you get to the MS. And 8.22 is greater than the critical value of 8.27, they rounded again, is greater than the critical value of 3.86 that we've determined earlier. Make sense?
What is the F?
The F is MS between, the standard error between, divided by the standard error within. Make sense? Are we all coming to the same result?
I'm kind of lost.
Why?
The whole last part, like you had me, so you did this some squares for the last one.
So sum of squares, which sum of squares did lose you or confuse you?
I have the n minus n squared, but all that stuff at the bottom, I don't know. Why.
Okay, wait, let's go through it. No, it's not fine. Okay. Does it work? No, no. Oh, yeah. Okay. You have sum of squares between. Sum of squares between is essentially the same as adding each of those up for all the number of participants, and you have mean minus grand mean. So this is the variability between. No, these are no calculations. This is the sum of squares that we calculated here. Totally within between.
Okay.
Degrees of freedom we have from here. We have determined that earlier. The MS is calculated by sum of squares divided by the degrees of freedom for between and within. And the F is MS between divided by MS within. Okay? You remember what I said so between is always going to be larger because it's smaller degrees of freedom and more variations likely with a smaller sample size. Yeah, and this is the Anova. This is all it was in broad strokes. In more detail, it's a little more, but yes.
Do you mind uploading this Excel sheet? The one that is on campus is like a little bit more confusing. Like I like how this is all in one on campus, like 4 sections.
Yes. So yeah. So you basically have degrees of freedom in the numerator. That's your groups. That's your degree of freedom between. So we have 4 groups. Degrees of freedom between is number of groups minus 1. So 3. If now we need to determine degrees of freedom within the denominator. So this is our degrees of freedom within. So our degrees of freedom within are degrees of freedom of group 1, group 2, group 3, and group 4. So the first group had 4 entries, degrees of freedom of 3. Degrees of freedom of group 2 were 3 entries, minus 1 is 2. And that's also true for 3 and 4. So we have 3 groups with 2, that's 6, plus the 3 from the first group is 9. So now we look, okay, so we have now 3 degrees of freedom in the numerator between, and 9 in the denominator. So now we go all the way down where we have 9. Degrees of freedom is 3. Our critical value here, corresponding to a p-value of 5%, is 3.86. Make sense? So we have 3 groups. Degrees of freedom total is 9, or within is 9. And critical value is 3.86. Yeah? If we look at 5%. And that's basically all there is to Anova. We will do in the practice lab and in our lab day, on our lab day, we will talk about how to compute this with R and how to interpret outputs from R. They look exactly the same way. Any questions to that? Any more questions? No?
I'm behind, so like.
Where did we lose you?
No, I just.
Where did I lose you?
I need to read the book. I want slower.
Yeah. Well, watch the recording. Go through the calculations will really guide you the way. Try to go through the calculations of what was done with each step. And this is why I think these Excel spreadsheets are so helpful, and I hope they really are, because you can go through all the steps together with the recorder. You can go through the steps, and this kind of helps you to materialize the approach. Make it a little bit more tangible. Did it go through? You got the same?
Yeah.
You want to review something?
No, she very clearly talked to me.
Okay, good.
Thank you.
Sure. Okay. So what are we doing now with this result? We know that the F value is greater than our critical value. We're comparing this now in a one-sided hypothesis test against the unimodal right-skewed F distribution. And our F value is greater than our critical value of 3.86. As a consequence, we're rejecting the null hypothesis, and we say that at least one group is significantly different. So these variances are essentially what we've seen. These are the calculations that we did, and now we want to understand the effect size. The effect size is calculated now by the sum of squares between divided by the sum of square total. And this is the so-called R square, which will also come back to us looking at correlation and regression, where we will calculate the R square as the so-called coefficient of determination. So the coefficient of determination in the context of R square means to make us understand to what extent a prediction of a certain value, as done with regression, allows us to explain the variability in a data set. So when you look at this, you have essentially you have a sum of square total, which is your overall variability, and you're dividing your variation between the groups by the overall variability. So this essentially goes in the same direction. So you're meaning to bring in context, and regression uses the same kind of way to quantify the explained variability. So you're explaining the variability between the groups by the variability in the overall sample. For regression, it's then the predicted, so the explained variability in relationship to the overall variability that you really see. So it goes in the same direction, and the underlying principle, how you quantify the predictive qualities of a regression model, is by using exactly this equation. But that's enough for now about this topic. We'll talk about this more later on. So sum of squares between divided by sum of square total is now 0.73 R squared. This is our effect size. I also urge you to look up for the other marker of effect size. There's an alternate marker of effect size is mentioned in the book. I think I excluded it from the quiz, but make sure to look at this alternate marker. It's a theta, which essentially accounts a little bit more for the sample size, but this is at this point not relevant. So the conventions for the effect size is 0.01 as small, up to 0.06. 0.06 to 0.14 is medium. Everything greater than 0.14 is large. Same conventions as per Cohen. So now what you're going to do with this knowledge, and this is, we will not calculate this, but this is just conceptually important to understand it. So when you have now a significant difference in your Anova, you know now that these four communities are different. What do you want to do based on this knowledge? You know that at least one is different. So now you want to know which one and why, and you want to dig deeper, you want to investigate more. So you're going to do now post hoc tests. Post hoc because hoc stands for the event. So the event here being is the Anova. So pre-hoc would be everything before the event, post hoc is after the event, ad hoc is during the event, on the spot. You may have heard ad hoc. That means at the event. So post hoc essentially means the Anova is taking place. You have found out that your Anova gives you a significant F. Now you know one is different and you want to compare. So you have two ways to do that. You go in and you use post hoc tests, or you do bland comparisons that you are interested in just for the sake of doing this comparison because you're interested in them. Both is legitimate. If the Anova is not significant, then there could be a debate whether it's really serving any point. but you can do it for just investigating a specific relationship that you want to investigate. So the post-hoc tests that we are discussing here, and there are more than that. So there are more tests. There's also a Dunnett test, and there are a couple of other tests. So we have a Tucky honest significant difference test, and we have a so-called Bonferroni correction. So the Tucky essentially calculates now the difference between each group, M1 minus M2, divided by the SM, divided by the standard error of the mean. By that, you basically get to an MS within divided by the N. This SM is calculated in that fashion, square root of MS within divided by the N. Gets you now to look up these comparisons here in the so-called Q table. And you can compare now your groupings. So you have within groups degrees of freedom, you have 9, and you have 4 levels, right? So you would now compare this against this threshold. That's one way of a post-hoc test. So you would do this for each of your groups. Secondly, you can also do a Bonferroni correction factor or Bonferroni test, which is basically you're making your hypothesis critical value for hypothesis testing more strict, and you do pairwise comparisons. So you compare group 1 versus group 2, group 1 versus group 3, group 1 versus group 4, etc., etc. So you essentially end up with 8 comparisons, I believe. So this, of course, is multiple testing. So you're inflating your alpha value, your type 1, no, not alpha value, your probability for type 1 error. So for this very reason, you calculate the number of comparisons, and this is which we did here in the beginning. Remember? Oh, this is terrible. Sorry, one specific one that I want to show you. Here the number of comparisons with 4 groups with 6 comparisons, not 8. Sorry. So we have a probability of a type 1 error of 27%, right? So as a consequence of that, so we have 6 comparisons. And what we're doing now, we essentially are, oh, here it is. Okay. We're basically, okay. Okay. So we have 6 comparisons, 4 means, 6 comparisons. We are dividing our alpha level of 5% by the number of comparisons. And we will only accept a hypothesis test as significant once it is smaller, once the p-value is smaller than this Bonferroni adjusted critical value of 0.08. Make sense? So that's how you counteract the inflation of your critical value, of your type 1 error probability. Good. So this is Bonferroni. Any questions about anything of the post-hoc test? If not, I think we're pretty much at the end. We've made use of our 1 hour, 15 minutes. So Wednesday we don't have class, right? I hope there's some low-key excitement. And we will continue on Monday with any questions from Zoom? Who's actually still on Zoom? Everybody still here?
It wasn't as spicy as I thought. It wasn't as spicy as I thought.
Wasn't that spicy? Good, good. I'm happy to hear that. Lizzie, Yael, any questions?
I'm good, thank you.
You're welcome. See you on Monday.
Thank you.
All right.
Thank you so much. Have a good
You too.